All right, how's it going, everybody? We are here. This is our first video for week two. It's Thursday, January 21st. We're going to be talking about section 6.3 today. And in section 6.3, we are going to look at computing exact values of trigonometric functions of only acute angles. Our next step in section 6.4, next video, is going to be computing trig values of any angle, right? Not just ones that are acute, smaller than 90 degrees. Right? So in a sense, what we're doing is we're trying to get a handle on what are these trig functions, sine, cosine, tangent, secant, cosecant, cotangent, and how do we evaluate them relative to the angles that they're operating on. What we're going to end up finding today is that there are only some special cases that we can actually perform this exact calculation for. And since those are, well, I'm calling those special cases for a reason, we're going to want to for sure identify those and know those exact values rather than just some decimal values that we're getting out of our calculator. Right. So our overall goal is to be able to compute trig functions of any angle. We're starting right now with sort of the easy ones, the 0 to 90 degree angles, and we're going to continue to sort of expand our definition of our six trig functions to better understand what it means to apply those trig functions to any angle whatsoever. That'll be happening in the next couple sections here. So in this section, we're only doing acute angles. So remember the definitions of acute and obtuse when it comes to triangles. Acute angles are angles that are less than 90 degrees. Right is equal to 90 degrees, and obtuse is greater than 90 degrees. So just a quick acute is less than 90 degrees. Right angles are equal to 90 degrees, and obtuse angles are the ones that are greater than 90 degrees. Right, so our goal today is just these less than 90 degree angles. So you should notice that this interval has strictly less than signs in it, not less than or equal to signs in it. That's for a really good reason. I mean, so far, but this will change. So far, our trig definitions are very much tied to the concept of being able to draw a right triangle. And since a right triangle is always going to have one 90-degree angle in it, out of the 180 available degrees, 90 of them are in the right angle, right? That means that there are 90 degrees remaining for the other two interior angles there, which means for any real reasonable triangle, you can't have another angle be 90 degrees because then you would just be making an open box like this, right? Here's my three sides, the bottom and a left and a right. Two 90-degree angles is too much. All I got to do is angle in a little bit though now, and now you can see that this will eventually like form a triangle up here, right? But it doesn't really make sense for us to draw a triangle with a 0-degree angle or with two 90-degree angles. Those are actually going to be kind of the same thing there. So we want to think about like how do we kind of extend our minds on this one? That one's going to be a little bit weirder. I will say that very technically, I don't think the 0 and 90 degree cases are covered in this section, but I'm going to lump them into this section because to me they do qualify as these special angles that we should be able to describe right here. So those will be included sort of by me. It's not like we don't discuss those. I think I just pulled them a little bit early. I think those are in section 6.4, but we'll get them today because this is a relatively short section anyway here. So again, we will handle the 0-degree and 90-degree cases today. They're just going to be a little bit weirder, but they're still going to follow the same pattern of reasoning as to how we find the others of interest to us today. And again, where we're headed is that in the next two sections, we're going to continue to expand our definition. We're going to, in a sense, alter how we think about what the sine, cosine, tangent functions are actually doing to help us understand how they can apply to angles that you don't necessarily see within a right triangle. So that's kind of the direction that we're heading here. Right? So the question is, how do we compute the exact value of trig functions by hand, right? So like, and by the way, you should be able to do these guys in your calculator right here, right? Like we can get decimal approximations. I should throw that word in here. How do we compute the exact value of trig functions by hand, right? And so what we can do is we can get estimates for each of these guys right here. We can estimate them with decimals in the calculator. And by the way, if you haven't done any calculator computations here, maybe now is a good time. Remember that you need to be checking the mode that you are in. So I'm seeing that the sine of 10 degrees is giving me 0.1736 if I was going to give 4 decimals there. Cosine of pi sixths, I need to move into radian mode to get this estimate here. cosine of pi sixths, I'm seeing a 0.8660. Tangent of 45 degrees. I need to go back into degree mode for this one. Tangent of 45. Oh goodness, it's just 1. Interesting. So it seems like maybe some of these are just giving us some weird decimals out there that we don't recognize, but it looks like some of these values are going to be nice and clean. And so, and what's even better is that there's some decimals out there in the world that are actually very easily representable by other quantities that are simple. Like, for example, 1/7. That decimal representation for it, if you do 1/7 in your calculator, I'm guessing you won't recognize the decimal. It's kind of a gross, crappy decimal, but 1/7 is an easy representation for it. So another thing I'm wondering is like, are either of these decimals things that I could have maybe recognized if I knew like how to build it exactly? Or are these just some like unfortunate decimals that we're never going to ever actually figure out, sort of in a sense, where they come from, right? Get a nice concise version of them. It's just a decimal that goes on forever. So, turns out we can only determine an exact representation for the value of trig functions of a certain small subset of special angles, right? Only a couple few can we actually say, I know exactly what the sine of that angle is, or something like that. And some will just say the best we can do is to get a decimal approximation. There's not a more convenient way to write that value. In this section, we'll identify how to compute the exact value of each of the following 6 trig functions for the following angles. So again, remember that we have 6 trig functions of interest: sine, cosine, tangent, and then associated with those, sine goes with cosecant, cosine goes with secant, and tangent goes with cotangent, right? So there's 6 trig functions. And here I'm listing for you 5 angles. You just notice these 5 angles in degrees are exactly the same as these 5 angles in radians right here. Remember that 2 pi radians is 1 full revolution. Therefore, if we only go 90 degrees, that's 1/4 of 1 revolution, and 1/4 of 2 pi is pi over 2, or pi halves right there, stuff like that, right? So these fractions are exactly the radian degrees that are exactly these, and I'm just saying we should be able to do all this stuff in both in degrees and in radians. So this isn't going to be too terribly difficult. It's really just going to depend on some geometry that's going to look a lot like what we did last class, but I do want you to stop and think about like the scope of what this really kind of means. I just suggested to you that there's 5 special angles of interest for us, of the acute angles. There are 2 different angle formats. There's radians and there's degrees. And there's 6 different trig functions that we want to be able to apply to each of these and know the exact answer. What that means is that our goal for today is to come up with 60 different trig expressions that you should be able to evaluate exactly without a calculator. And that's kind of a lot. And that's just for one quadrant, right? That's only like our upper 90 degrees right there. We've got 2 or 3 other quadrants to go. So in a sense, it is sort of the case that there's like 240 different trig expressions that you are expected to be able to evaluate by hand without a calculator within like a week. And so in a sense, you should sort of be panicking right now, except don't do that. Do I expect you to memorize 60 small things? Definitely not. What our goal is to come up with ways that we can intuitively remember just a tiny bit of information and allow that to sort of fill in a ton of gaps for us so that we don't have to memorize 60 things, or even worse, 240 things. We want to memorize like about 3 or 4 things and then allow that knowledge to take us the rest of the way. I promise you, my goal is for us to have to do as little as possible memorization work. But at the end of the day, it is definitely the case that you are expected to, like in a sense, memorize a way to know these exactly. But this isn't by memorizing 240 different things. That's not the way that anybody goes about this. So it's not what you're expected to do. But we want to, again, develop some intuition about this. Right? We want to figure out how do we know these, because if we know how do we know these exact values, then that will make it very easy for you to remember these in a pretty simple fashion right here. All right. So again, we're going to end the day with a table, and it's going to have 60 different values in it, exact values, not decimals, that you're expected to know. And again, we want to come up with intuitive ways that this is going to actually happen for us. Right. So let's start here. Special case number. So by the way, here's our 5 special cases: 0, 30, 45, 60, and 90 degrees. These are the only angles in 0 to 90 where there exists an exact formula. Okay, where there exists an easy exact formula. We're going to find later this semester, in like a month or so, that we can actually get some things like sine of 15 degrees because it's half of 30, but those are going to be a bit more complicated. They're going to take some work. So nobody considers sine of 15 to be like a 15 degrees, to be like a special angle that we like know, but it turns out that we'll be able to do some work to get an exact form for its representation as well. But again, that's kind of a later topic here. So for today, these are just our 5 angles. We just want to do it both in radians and degrees. So what we're going to see today is that 45 is sort of its own standalone guy right here. 30 and 60 are going to be partners together. And the reason for this is because in a right triangle, if one of your angles is 30 degrees, then the other one is 60 degrees. So both of these are going to be described by the same triangle. So those will be partners. And then similarly, 90 and 0 are both going to be awkward for the exact same reasons, because you can't have two 90-degree angles in a triangle. You can't have a 0-degree angle in a triangle. So we'll talk about those two sort of together as well, because the issue with them is sort of the same thing. So we're going to start with 45 just because it's the only like solo one right here. And the question I might ask you right away is, well, why doesn't 45 have a partner like 30 and 60 and 0 and 90 do? Well, notice that 0 and 90 are complementary. They add to 90. 30 and 60 are complementary. They add to 90. What's 45's complement? It's also 45. So it's sort of like we're doubling up this one also. It's just that it's itself is its partner pair right there. So special case number 1, 45 degrees, also known as pi-fourths radians. We'd like to be able to identify the values of all 6 trig functions being applied to this angle. To do this, let's just try to draw a representative triangle with a 45-degree angle. So our goal is to identify these 6 values here. Notice all I'm doing here is saying things like the sine of 45 degrees is the same thing as sine of pi-fourths radians. We want to know what the sine is of this angle. So here's our 6 values, regardless of whether it's in degree or radians, that we're looking to come up with for special case number 1 right here. So what I'm going to do is I'm going to go ahead and draw for myself a right triangle, and I am going to put just a 45-degree angle in it. Come on. What in the world? Why is my pen doing this to me? Oh, is it because I wasn't clicked on it? Hey, there we go. My pen has been obnoxious for me today for a couple stupid reasons. I was hoping it wasn't going to do anything wrong there. So there we go. Hey, that's one of my better right triangles. A little wonky over there. Those are some good perpendicular lines. I used to be a master shape drawer on a whiteboard. I don't get such good shapes with my pen and my stylus here, so feel free to mock me. So here's my 45-degree angle right here. I'm going to drop in that 45 degrees right there. Right. So my first question to you is, if that angle is 45 degrees, it must be that the other is also 45 degrees. Right, so that's going to lead me to draw my second triangle. And so this is maybe like a little bit overkill for drawing like triangle after triangle after triangle here, but I'm trying to sort of like make sure that there's a visual representation for my thought process here, rather than exclusively having my thought process be in words. So that's kind of why I'm trying to draw this out long form here. So the special thing about 45-degree angles is that if there's one of them in a triangle, it has to be the case that there's another one in a right triangle, I should say, that the other angle must be its complement, and 90 minus 45 is 45 again. Now, the other special thing that we can identify is that if a triangle has 2 angles that are equal to each other, then it has to be the case that the side lengths that are opposite of those angles must be equal in length. If we've opened up the same amount 2 different times, then we must have opened up a gap that's the exact same distance across both of those times. I think that's a pretty reasonable geometry argument for us to be making right here. So opposite sides must be equal length. This is going to allow me to draw my next triangle here. And so, I don't have a size of this triangle. I just know that it's a 45, 45, 90 triangle. But I know that these side lengths must be equal to each other. So instead of labeling my legs A, B, and C, I'm going to label them A, and C, because I know that the 2 A's are equal in length to each other. Now, the final statement that I want to make is I remember I'm trying to like compute some like numbers here, right? Like I want to know like what number do I get by taking the sine of 45. As it stands right now, the sine of 45, sine is opposite over hypotenuse. Right now, I'm just getting an answer of a divided by c. That's not satisfying to me. I want it to be based on that actual ratio of their lengths. So the thing that I know is that when I'm computing all of my trig values, those are all just ratios. And those ratios are going to be maintained whether we have a giant triangle or whether we have a super tiny triangle. So the point is, I can just pick a number for A or for C right here, and we can just solve for what the other ones must be. Even though that will only be one example of a 45, 45, 90 triangle, it should be the case that all 45, 45, 90 triangles have all the exact same trig ratios because they're ratios. So if we scale it up, scale it down, the largeness of it will just get cancellation of our fractions, and the fraction, the ratio of the side lengths will be the same. So I'm going to say we only care about ratios. So we can pick any value for A. What's the nicest number on earth to do math with? 0. But I don't want to pick a leg to be of length 0. So I'll pick the second nicest number on earth to do math with, which is 1. So what I'm now saying is I'm thinking that if that side length is 1 and that one's 1, if this is 45 and that's 45, there's my right angle. My last question is, what's C going to be over here? And so I've got 1 squared plus 1 squared equals C squared. 1, that's just 1 plus 1. So that's 2. And I'm going to take my square root. So it looks like this should be a square root of 2 as my third leg for that guy right here. So the point is this. This is one particular 45, 45, 90 triangle. But what I know is that even if I scaled it up or scaled it down to be much bigger or much smaller, if you would take any ratio of any two side lengths, the ratio would be exactly the same no matter what. So I'm okay with the fact that I picked a particular one triangle, the 1, 1, root 2 triangle, because the ratios of side lengths, which are exactly all of our trig functions, are going to be maintained here. So let's go ahead and do it. We've got the triangle that defines a 45-degree angle description for our trig stuff here. So sine of 45 degrees. I'm going to just think of this 45 down here, as, and the bottom one, as my angle that I'm sort of viewing this from. I know that sine is opposite over hypotenuse. And regardless of which 45 I pick, honestly, opposite is 1 in both cases, and hypotenuse is root 2 in both cases. So I'm going to get 1 over root 2. Okay. What's the cosine of 45 going to be? Well, this sort of makes sense to me that this is going to be the exact same thing because cosine of 45 is going to be adjacent over hypotenuse, but the whole point of this 45, 45, 90 triangle is that opposites and adjacent are equal to each other. Right? So it looks like I'm also going to get 1 over root 2 for this guy here. This is opposite or adjacent over hypotenuse. Right? Now, finally, I know that tangent, I can either think of this as opposite over adjacent, or we also know that this is sine over cosine. You should notice that sine of 45 and cosine of 45 are exactly equal to each other. And whenever you take a number and divide it by itself, you're always going to get 1. You should notice that opposite over adjacent here is in fact 1 over 1. So that's, that seems like that's going to be 1 to me. Either way we look at it, either as opposite over adjacent, the direct ratio, or as tangent is the ratio of two other trig functions is also acceptable. Now, coming over here, I know that cosecant is just the reciprocal of sine. Secant is the reciprocal of cosine. Cotangent is the reciprocal of tangent. So I don't even need to look at the triangle for these ones. I'm just going to flip my fraction. This should now be root 2 over 1, which is just the same as root 2. Also root 2 over 1. And this guy, this was like a 1 over 1. We're flipping it, and we're still getting 1 over 1. So it looks like cotangent and tangent are both equal for this guy for 45 degrees right there. Right? So there we go. We did our first one right there, right? So all we did is just drew a triangle that had a 45-degree angle in it and decided what must be true. If one angle is 45, then both are 45. If both angles are the same, then the opposite side lengths are the same. Since we're only interested in computing ratios of side lengths, I don't care what the actual value of them is. The ratios will be maintained by any size. So I just picked any old number I wanted for one of the side lengths and determined what must be the related associated side length here. So there's two small things I want to do before we walk away from this one right here. One, I want to point out that you will pretty much never see your book reference this number 1 over root 2, even though it's going to come up like a million times this semester. The reason is because most math nerds really don't like having irrational numbers in a denominator down here. Irrational meaning square root of 2 is just not a number that can be nicely represented any other way. Its decimal expansion is infinitely long and non-repeating. And so a pretty typical thing to do. So one of the things I'd like to do, how much room do I have there? Okay, that's enough. Is to rationalize the denominator. So 1 over root 2. You know what I should do? Hang on. Let me do this. I just want to use a little bit more color these days so I can be a little bit more visible here. So let's rationalize the denominator. So this is something that you should do this semester. It's not like necessary, but it's definitely how everybody on earth that's ever going to do math is going to write things. And again, nobody, if you ever ask a math professor ever what sine of 45 or what sine of pi fourths, there's no math professor on earth that will say to you 1 over root 2. Not a single one. Every single one of them in their mind has this memorized as the version with a rationalized denominator. And so what I'm going to do here is I'm going to take this 1 over root 2 and I'm going to say, I don't want this to be square root of 2 anymore. I want it to be some rational number, some not square root number. Well, what would you like to do to square root of 2 to make it a nicer number? The nicest thing you could do to square root of 2 is square it, right? Now, squaring is really just the same thing as multiplying a number by itself. So what I want to do is I want to multiply the denominator also by the square root of 2. But what we know is if I just multiply the denominator by root 2, then this is a different number now. So what's the only number you're allowed to multiply by without changing the value of a previous value? What's the one number you multiply by and it doesn't change anything? And that's 1. 1 is any number divided by itself written in fraction form. So basically what I'm saying is I'm going to multiply 1 over root 2 by 1, right? This is just equal to 1 right there. Root 2 over root 2 is 1. So I know that by multiplying by 1, I'm not changing the value of the number. I'm just changing how the number looks. So what I can now see I have on top is 1 times root 2 is root 2. We've sort of moved the irrational part to the numerator. That will be better for us for algebraic purposes later. And on the bottom, square root of 2 times square root of 2, that's square root of 2 squared, which is just 2. So it is going to be the case that every mathematician on earth, when you ask them what the value of sine of 45 is or the cosine of pi fourths is or whatever, they're always going to tell you it's root 2 over 2. Nobody ever thinks of it in terms of 1 over root 2. It makes it difficult to combine those numbers later when you have I know that dealing with fractions is annoying enough in life. The last thing you want is denominators that are square root terms. It makes combining fractions much, much, much more annoying, right? So 1, that's my kind of rationalization there. And there's nothing to do here. 1 is the number 1. There is no better representation for that. Root 2, I don't have any way to alter that. Technically, that's the number root 2 over 1. It's rationalized in the denominator, just like we want. Right? Another thought that I have here that I just kind of want to generically say is every 45, 45, 90 triangle has side lengths in proportion with 1, 1, root 2. That's always going to be the proportions of the side lengths of any 45, 45, 90 triangle, whether it's the biggest or smallest one in existence or just the one that's on the page right now. That ratio those relationships between the leg lengths will always be maintained right there. We're going to be able to make some very similar statements for our next guys that we look at right here. Right? So we're going to do a very, very similar thing to get our other special cases out here. This was our 45-degree angle. We now want to do the same thing. Let's do our second grouping of the special cases. The 30s and the 60s go together because we can make a 30, 60, 90 triangle. That adds up to 180 degrees, just like we want here. So same deal. We're just getting two different sets of them. So notice I have my 30s and my 60s laid out for us right here already because we're going to find the two different groupings together here. Right? So let's do that. Special case number 2. So here's kind of my issue with this one, is this. I have less information in this case here. Let's start with, wait, get back to black here. So let's start with just the 30-degree angle, right? Oh my goodness. Try that again. So the first thing I want to do is just kind of mimicking what we just did up above right there. Imagine that we were only told one angle. I'm saying to you, hey man, I got a right triangle with a 30-degree angle in it. That's all you know. Then the first thing I would think to myself is, other angle must be 60. Right? 30 plus 60 is 90, plus the 90-degree angle makes 180. Right? So here's my dilemma though. What we did before is we knew that because the angles were the same, the side lengths are the same. Unfortunately here, although one angle is double the other angle, it's not necessarily apparent to me that that means a side length is going to be double the other side length. That's just not geometrically a true statement right there. So I sort of am in a pickle here where I have slightly less information than I sort of want. All right, I'm going to go ahead and label these our A, B, and C like we got them right here. But we don't know quite as much as we knew in the 45 case, right? If the angles are equal, the opposite sides have to be equal. But if one angle is double another angle, that doesn't mean that the other side length is double the other angle. That's kind of a problem for us that we're missing a piece of information here. So we're going to need to be geometrically slightly craftier in finding how we're going to do this here, right? So one thing I'm going to say is that one piece of information that we do get from our previous special case, or one technique, is that, again, our goal is only to discuss the ratios of the side lengths. So we can sort of just pick a size that's convenient for us. And what I'm going to say is a convenient size that we're going to end up seeing here for ourselves. So this is one of those things where like I know a little something about where we're headed with this. So I'm going to pick a nice number with my pre-knowledge right now. Even if I didn't pick a nice number, we'd still get everything to work out the exact same. We would just have one extra simplification step. So I'm just helping us avoid one step of algebraic simplification later by picking a smart number here. I'm going to say only care about ratios. That means that we can kind of just choose a leg length. Now, obviously, I can't just choose necessarily even two of these leg lengths because the relationship between two of them should be dictated by the angle. And since I haven't decided what these angles sort of mean to me yet, at this point, I can really only pick just one of these. I can make a statement like C is 2, and I can decide A and B need to be whatever they need to be for C to be 2 and for us to have those two angles. But I can't even go so far as to also say what I think A or B must be. I need to use my angle information to help me out with that. So all I'm doing is just getting to here then so far. So I still got my A, still got my B, but I'm going to call C2. This is my larger angle, so it's 60, smaller angle is 30, right angle right there. So now what I'm going to do to sort of help myself kind of figure out the stuff that we've got going on right here is I am going to mirror this over itself. right? So now what I'm seeing here is that's 60 and that's 60. That's a right angle and that's a right angle. This is length A and this is length A. But notice now on our external parts, that's 2 and that's 2. This height right here is the height of B. And importantly, very importantly, you should notice this is 60 degrees. Right there. So here's the thing that I'm finding. Right, and there's my B. So what I just discovered is that if I mirror image this 30, 60, 90 triangle over itself, then I'm actually getting a 60, 60, 60 triangle, right? This external triangle here is not a right triangle anymore. It has all three angles are equal, therefore all three sides must be equal. So 2 is the same as 2 is the same as 2a. Notice that the length of this side over here is now 2a units long. Right? A plus A is 2A. Right? So apparently A is 1. It has to be. I know this from just a little bit of geometric playing around right here. I'm mirror imaging over. I got a 60, 60, 60 triangle. If all three angles are the same, all three sides are the same, two of the sides I knew were the same, 2 and 2, and I had the bottom down there was 2 copies of A next to each other. So it was 2A long. So A has to be 1, or else this isn't an equilateral triangle. And I know it is. I'm looking at the angles in it, right? And so now we can solve for the last one, but the Pythagorean theorem, right? Now I'm kind of back to my triangle right here. So now I'm going to do the Pythagorean theorem, and I think we're good to go. So now I've got 1 squared plus b squared equals 2 squared. And I'm getting 1 plus b squared equals 4. B squared equals 3. And I'm seeing that b is the square root of 3. So we were able to identify all three of the angles associated, or all three of the side lengths associated with this guy here. Maybe I'll get a different color here to draw this guy. So that's our bigger angle. So it's 60, smaller is 30, right angle. We just decided that A, if C is 2, then A must be 1. And if C is 2 and A is 1, then B must be root 3. So this is the only other right triangle where we can determine exactly what the side lengths must be in ratio only by knowing the angles. We did the 45, 45, 90, and we got our 30, 60, 90. These are the only two right triangles that there are where we are guaranteed to know the side length ratios by only knowing the angle ratios in like an exact form right here. Right? So we want to use that purple triangle there now to answer all of our questions, right? All we have, the hard part here is building the triangle. Now I'm hoping that the easy part is just stating the values for the 30s and the 60s right here. So again, we should be able to just get the 30s and then reciprocal to get the other 30s. And then we'll do the 60s and reciprocal to get the other 60s that are over here, right? So sine of 30. Sine is opposite over hypotenuse. So sine of 30 relative to 30, opposite over hypotenuse is 1 over 2. Wow, that's pretty nice. It worked out to be a 1/2. Cosine of 30. And by the way, cosine of pi 6, I want to kind of point out to you real quick. We went and did this in our calculator a second ago. We got some crappy decimal for it, but it turns out this crappy decimal is actually a pretty nice clean square root fraction right here. I know square roots and fractions don't make you think clean, but like it's better than just some like arbitrary decimal that you don't really have a good way to describe. It turns out that this decimal right here just really doesn't have a clean form, and this one actually does. And that's just, you can't tell that by just looking at the decimal, right? So we're sitting here at the pi sixths, right? So pi sixths here, cosine of 30 degrees, or cosine of pi sixths. Cosine we know is adjacent over hypotenuse. And so cosine adjacent is root 3, hypotenuse is 2. So square root of 3 over 2. So you can now go back to your calculator and double check that if you do square root of 3 over 2, it gives you the exact same result as if you asked it what's cosine of 30 degrees or cosine of pi 6. Those are apparently the same as each other. Finally, we can look at tangent here. We know that tangent is opposite over adjacent. Opposite of 30 is 1. Adjacent to 30 is root 3. So we're going to get a 1 over root 3. But the same thing before with our 1 over root 2. Nobody ever really writes this one this way. Everybody will always rationalize this guy right here. And so we do 1 over root 3 times root 3 over root 3. That's me multiplying by 1, so that's legal. And that gives me root 3 over just regular old 3 right there. So much, much more common to refer to that as root 3 over 3. Also remember, we totally could have just done the division with sine and cosine. Notice here, 1 over 2 over root 3 over 2 just leaves us with 1 over root 3. The dividing by 2's cancel from sine to cosine if you did that division right there as well. So cool. So we're kind of, we're cruising along right here. We know that we just have to flip our fractions to get their partner versions. Sine is partnered with cosecant. Cosine is partnered with secant. Tangent is partnered with cotangent. So let's just take all the reciprocals right here. This will become 2 over 1, or just 2. This will become 2 over root 3. Again, we're going to want to rationalize this thing here. So a little more typical to write that as 2 root 3 over 3. Again, not totally required, but definitely how you're going to end up seeing it in the book and everywhere else online. And finally, cotangent we can flip. And notice if I flip my simplified version over here, that's sort of not what I want, because then it's going to have an irrational denominator again. I'm just going to flip this version of it. So this should become root 3 over 1, which is just square root of 3. Cool. Let's do our 60s, and we're good here. We're going to get kind of all the same stuff, right? Now, one of the things I want to remind you from last class is we talked about the fact that the sines and cosines seem to have these almost agreeing things, but they had this complementary property where we made some statements that were like sine of theta equals cosine of 90 minus theta, right? Well, that's exactly what we're doing now. Sine of 60 should be the same thing as cosine of 90 minus 60, which is cosine of 30. Well, we already did cosine of 30, and we found it was root 3 over 2, so we'd better get root 3 over 2 in this slot right here. Our complementary angle identities already showed us this last class, right? Now, when I go to look at my triangle here, sine of 60 degrees, opposite over hypotenuse for sine, yep, it's root 3 over 2. Similarly, just like cosine became sort of switched to sine here, we're going to get the exact opposite thing here. Cosine of 60 should be sine of 90 minus 60, which is sine of 30. We're going to get 1/2. So cosine of 60 is adjacent is 1 over hypotenuse is 2. It's 1/2, exactly like we expected. Right? Tangent of 60, it's opposite over adjacent here. Tangent of 60, opposite over adjacent. What do you know? We're getting root 3, exactly what the cotangent of 90 minus 60 is. All right, we got that one right here. We just got that root 3 over 1. And now we just get to flip all these to get their partners over here. So we're going to get a 2 over root 3, which we have already above determined to be equivalent to 2 root 3 over 3. Secant of 60, we're going to get the flipped version of 1/2, which is just 2 over 1, or 2. And finally, 1 over root 3, we could flip that and get, or sorry, root 3 over 1, we're going to flip and get 1 over root 3, which again, we have already determined up here to be equivalent to root 3 over 3. So like notice that we've built a lot of these up really quickly here. I told you that we're going to have to get 60 different values today, and this is 12 of them, right? Because when I say 60, I really mean for both degrees and for radians. So here's 12 of them we already got. Here's 12 of them. Here's 12 of them. We've already got 36 of them done out of the 60 here today. So I promised this wasn't going to be too terrible right here. The bottom line is, like, if you know just this triangle, you should recognize that this is giving you 24 different trig values that you are expected to know. Just knowing just this purple triangle tells you 24 different quantities that I expect you to have essentially memorized and could come up with without a calculator. All you have to know is just the triangle, and you've got it all. Same thing up here. If you just know that 45, 45, 90 triangles always have side lengths of 1, 1, root 2, then you know all 12 of these values right here by default. So in my mind, I always come back to these triangles. If I were to ever forget these values, which I have been beat over the head with a trig stick my entire life, so I know these, I don't need the triangle anymore. But if you're learning these for the first time, all you need to know, that if we're talking about what the least you can memorize and still know all this, I think it's just the triangle. Know that triangle, and that's like most of all of our special angles that are out here. All right, so that's really, really convenient for us. So let me make that kind of that statement at the bottom again. That is every 30, 60, 90 triangle has side length proportions. So opposite of the 30 side, opposite of 30 is 1, opposite 60 is the square root of 3, and then opposite of 90 is 2. So I'm just trying to keep these in order right here. 1 root 3, 2. And by the way, I want to come back up to another statement I said up here. Up here, I was saying, just because this angle of 60 is double this angle of 30, it doesn't necessarily mean that B is double A. And it wasn't. Square root of 3 is not 2 times 1. It's root 3 times 1. It was sort of this weird in-betweener amount right there. So we were seeing here that doubling an angle does not associate with doubling a side length, right? So that was important that we didn't try to make that claim in our original triangle right here. That was incorrect. Right? So we got to kind of watch out with some of those geometry statements sometimes that we want to make that aren't quite right. But again, knowing this triangle is huge. It's going to give you so many of the values that you need to know this semester exactly in their exact forms as we've got them here today. So that's almost it. The only other special case that we have that we need to kind of work out for ourselves is the 0 degree or 0 radian case and the 90 degree or the pi halves radian case right here. And if we get these, then this is sort of our job for today was to do this. We'll then just look at some examples of using these values and we'll call it a day. So our issue though is this. We'd like to be able to identify the values of all 6 trig functions being applied to these angles. To do this, let's try to draw a representative triangle. Well, that sort of doesn't make sense, right? At least, well, whatever. How do we make a right triangle with an angle of 0 or with 2 angles of 90? Again, here's 3 sides, 2 sides and a bottom. Well, that's what it would look like if you did 290s right there. They would just go vertically up forever, right? You have to have an angle of less than 90 degrees to ever form a triangle, right? And even if it's a bare smidge less than 90, you can still make that happen right there. We have to be a little imaginative with this and be okay with getting really, really close. We will justify the approximation that we're making today more thoroughly when we kind of update our definition of how we define our trig functions in the next couple sections. So this is me saying, expand your mind a little bit, like think about this, and you'll kind of generally agree with where this is heading. And we will see with a new definition of how to think about sine, cosine, tangent in the next couple videos here. We'll see that the answers that we're going to get right now perfectly agree with our a little bit more robust definition that we'll be getting in the next couple sections right here. So this is, in a sense, a little hand wavy, but it's also correct. So this is a thing we should do. So here's what I want to do. I'm going to draw a triangle that has like really, really, really close to a 0 degree angle and a 90 degree angle in it, right? Let me get back to my black pen here. So here's my triangle of interest. Right? What I'm trying to draw here is something really, really, really close to this also being 90 degrees. Right? I'm going to call that theta and call that phi, just because I can't write inside of this triangle very well. Theta is almost 90 degrees, and phi is almost 0 degrees. I'm trying to draw like a super extreme triangle right here, like crazy extreme. Like how extreme? Let's just say this. I'm going to label these A, B, C. And let's make this an extreme triangle. I want to make the side length b 1,000, but let's only make a 1. All right. So what's going to happen here is I'm going to get that a squared, 1 squared, plus 1,000 squared equals c squared. And what you can see is that this is going to be, c squared is just going to be super close to also being 1,000, right? Because it's only literally one more and then retaking the square root again. So you're going to get something like 1,000.001 or something like that. Like it's going to be really, really close to 1,000 right here. So c is almost like 1,000 as well. All right. So the triangle that I'm picturing for myself here, the triangle that has a 90-degree angle, I'm thinking of theta as like a 90-degree angle, although it can't technically make a triangle. I'm thinking of phi as essentially a 0-degree angle, even though it couldn't make a triangle. I'm thinking of a being 1, and I'm noticing, and I'm really thinking of a being like 0, right? Like the whole point is if phi was truly 0, then there wouldn't be any side length. So I'm picturing a being tiny, 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 tiny. And if that's the case, then those lengths of B and C that you're looking at right there, those are going to be almost exactly the same length, like super close to being exactly the same length, right? So what that means to me is that my approximate triangle I mean, it's going to be more or less like this, right? Where this is going to be our like 90 down there, and that's going to be like our 0. Now, technically, that's not a geometrically correct shape, right? But again, this is where I'm saying think about like 89.999 degrees and 0.0001 degrees, right? Like technically that is a real triangle that we could build. It's extreme in its angles, but it's technically appropriate to do that. So think of getting very close to 90 and very close to 0 for those two angles. We will have side lengths that are, if 1 and 1,000 are the two legs, then the hypotenuse will be very close to matching that value of 1,000 right there that I'm using, right? So using this, we want to kind of use our imaginations to stretch it the rest of the way. Use our imaginations to take us from 89.999 to actually 90 right here. And so we'll do that in these values that we're getting out here. So what I'm going to do in these cases right here, honestly, what I should do is get rid of these equal signs. I don't want equal signs in these things right here. But I want to say that like relative to the triangle that we're building, what does it look like we should be getting for sine of 0 degrees? Well, relative to where we have our essentially 0-degree angle, sine is opposite over hypotenuse. That looks like 1 over 1,000. But what I know is that that one is going to get even smaller as our angle goes to 0. This is a really small number getting smaller. This is going to be 0 right there. The sine of 0 is going to be 0. You can verify that in your calculator right now. On the other hand, when I do cosine of 0 is going to be like 1,000 over its almost identical 1,000. And the closer and closer our angle gets to 0, the closer and closer that leg and the hypotenuse will be to the exact same length. And when we divide two things that are the same, we get 1. Finally, to get tangent of 0, I'm going to do my opposite over adjacent, and I'm going to get 1 over 1,000 again, right? And so that's going to be our thing that's going to 0. And really, again, I don't want to be claiming some equalities out here that aren't true. We are definitely making like a sort of an estimate and then allowing to think ourselves of saying sort of taking a limit, like letting things go as close as we can imagine them going. So these really are our appropriate values right here. And remember that tangent of 0 is going to be sine of 0 over cosine of 0. And so that's also what's telling me that this should be 0 over 1, which is 0 right there. Cool. So now we've got to think to ourselves, well, what's up with cosecant? Well, cosecant should just be the reciprocal of this. But what does this mean? This is like 0 over 1. How do you flip 0 over 1? It becomes 1 over 0. We're trying to divide by 0 now. That's a problem. So this guy right here is going to be undefined. Right? It's a division by 0. Right? Secant I think we're going to be okay with here. It should be the reciprocal of the number 1, which is just 1. I flipped 1 over 1 and got 1. Again, similarly, to take the reciprocal of 0 doesn't make sense. This is like 0 over 1, which gives us 1 over 0. So it's undefined for the exact same reason right here. So it seems like it doesn't make sense to take the trig function, apply it to literally any angle. Some of them have undefined quantities. In section 6.5, we're going to look at some graphical representations of these, which will really help you visually see why those quantities don't make any sense once we get a graph in one of our upcoming sections right here. So kind of as we learned up above, we expect that when we flip to our complementary angle, right here we saw all the 30s, all 6 of them. When we flip to our complementary angle, we got all the exact same values back again because of our complement rules down here. We're going to expect to see that same thing down here. We just talked about all the zeros, and basically we got answers of 0, 1, and undefined. We're going to get those same answers down here, 0, 1, and undefined for all these guys. Right? So now we're looking at sine of 90. Sine of 90, that's opposite over hypotenuse. Opposite is 1,000, hypotenuse is 1,000, so this is going to get us towards 1. Cosine of 90, that's adjacent over hypotenuse. That's 1 over 1,000, but that 1 is like infinitely small, so it's more like 0 over 1,000. That's getting us to 0. Tangent of 90. Well, I know that tangent is sine of 90 over cosine of 90, and that seems to be a problem for me. Cosine of 90 is 0, so that's like 1 over 0. That is undefined. And again, when we get our graphical representation of this in a couple days, you'll see a very clear picture as to why the tangent does not make any sense to be applied to 90 degrees right there, or to pi halves. And again, we're just taking some reciprocals. The reciprocal of 1 is 1. The reciprocal of 0 is undefined. And it seems like the cotangent is okay now, right? If tangent is opposites over adjacent, then cotangent is adjacent over opposite. Adjacent over opposite right here is going to give us that 0 over 1, or just 0, right? Flipping 0 over 1 gives us 0 for our cotangent of 90 right there. So again, this is kind of a hokier triangle. And before, I think that I very much do want to emphasize to you, listen, like those 45, 45, 90 triangle and that 30, 60, 90 triangle, those are worthwhile to just memorize, know what their side lengths are. That's going to be the least memorizing you can do to get a ton of good information. This is kind of a hokey, crappy triangle that's not really a real triangle right here. So if you feel slightly uncomfortable about some of these values, that makes sense because that's not a real triangle that they're coming from, right? But what is going to happen in our next 2 sections is we're going to slightly modify how we define sine, cosine, tangent, cosecant, secant, and cotangent to not be exclusively needing to be defined based on a triangle, but being more open to being defined based on any angle. And in section 6.5, we're going to talk about how this closely relates to circles, at which point we're going to see exactly why this makes sense to talk about these trig functions being applied to any angle, obviously with the exception of some of these undefined cases right here. And again, we'll get a very good visual estimate for where those lengths are in a picture, and that will help you to see why we're getting some zeros, some ones, some undefineds from these guys over here. So I guess this is still, in a technical sense, I guess a worthwhile triangle to remember, except that it's like wrong in a sense. All these numbers down here are right. We didn't get anything wrong down here. Obviously, that's just a weird triangle right there. So I don't know that I want to make any final sentence down here. It's like any triangle, any 0, 90, 90 triangle has side lengths of 1, 1,000, 1,000. Like that's not really how that works. But I'm not going to conclude that. But we will get these zeros, ones, and undefines whenever we are a 0-degree angle or a 90-degree angle, our perpendicular angles right there. So this is good. We did it. We just came up with, another 24 right here. So 24, 24, and 12. We just got all 60 of the values that we were interested in here today, which is pretty cool. So let's kind of reference some of these back here and see how we can just do a little bit of algebraic statements for some of these guys right here. Get some exact forms of some answers. I think we're just going to do, just 3 of those examples and then kind of summarize what we saw here. So let's remember back to these things. Sine of 45. In my 45, 45, 90 triangle, I'm always going to remember that both sine and cosine are giving me that root 2 over 2 value, right? So we're looking for sine of 45, and there's sine of 45. We got root 2 over 2. That's my first one here. And again, our goal is to memorize these. You should be memorizing these. Every one of these you are expected to know. So I am thinking that I'm going to write this as 8 times root 2 over 2. Cosine of 30, it's in my 30, 60, 90 triangle. I know it's going to involve the numbers 1, root 3, and 2. If you haven't memorized them yet, which I don't expect because you're watching this right now, that I got to go kind of like maybe look this back up. But my cosine of 30 is going to be root 3 over 2. Sitting right there. Cosine of 30, root 3 over 2. So now what we'd like to do is do a little bit of algebraic simplification to make this a little bit nicer for ourselves. 1, remember that any standalone number is really itself divided by 1. It looks like I'm going to be able to do some cancellation here. So here's kind of some things I'm thinking. Some other simplification we can do. Another thing, when you multiply two numbers together that are both underneath square roots, it is the case that we can do this multiplication underneath the square root, meaning rewrite this as the square root of 6. Right? So 2 times root 3 is root 6 times 8 is still up in the numerator. Denominator, 1 times 2 is 4. And it looks now like I can do a little bit more cancellation and rewrite this as 2 root 6 right there, right? The 8 and 4 doing a little canceling, getting us to 2 root 6. Okay? There's our first one right there. These were in degrees, as I've been verbalizing everything today. Let's remember that we are absolutely expected to know our radian measures as well for these things. So tangent of pi fourths. I'm remembering that pi fourths is the same as a 45-degree angle. I know that in 45-degree angles, my sines and cosines are equal to each other. And I know that tangent is sine divided by cosine. And so if the sines and cosines are equal, and tangent's the ratio of them, then the tangent of pi fourths should be 1. And if we look back up here, tangent of pi fourths is 1. Right? Tangent sine over cosine, and at 45 degrees, both legs are the same, so the sine and cosine are the same, and tangent is their ratio. And the ratio of two identical things is always 1. So this is going to give me 1 minus. Now we need sine of pi thirds. Pi thirds is the same as 60 degrees, right? Pi sixths is the small one at 30. So there's 30, 45, 60, and 90. Those are the ones that we care about. I can fit it perfectly into the frame. 0, 30, 45, 60, 90. Pi thirds is the same thing as 60 degrees right there. So I'm picturing the sine of 60 degrees, and coming up here, sine of 60, it looks like it's that root 3 over 2 value right there. So if I wanted to get one nice expression for this guy right there, I guess this is fine. If we want to combine this, think about combining two fractions, we need to get a common denominator. So here I would be inclined to rewrite the number 1 as 2 over 2 minus root 3 over 2. So I can write this as 2 minus root 3 over 2. Although I should say, in this case, I absolutely expect you to do the simplification to get to 2 root 6. Whereas over here, I'm not so uncomfortable about that minus sign being right there. This seems like an equivalently acceptable answer right there. I just wanted to do a little algebra since I'm assuming a handful of you need a refresher on things like adding fractions, especially when it's a whole number plus or minus a fraction there. All right, our last one here. Tan squared of pi 6 plus sine squared of pi fourths. One very important thing, notationally speaking here, is to recognize that when we write things like sine squared of theta, that's the same thing as me doing sine of theta and then squaring. The sine operation will happen first. The squaring is sort of our outer operation in that case right there, the second layer of operations that we're doing. So here I want to find tangent of pi sixths. I want to find sine of pi fourths. I will individually square my answers and then I will add them together. So tangent of pi sixths, remember that pi sixth that's like our smallest important angle, therefore it's 30 degrees right there. And we saw this one, tangent of pi sixth, there it is. We got root 3 over 3. And that's getting squared. The next one here was the sine of pi fourths, remembering that pi fourths is our 45-degree angle here. I remember that with my 45-degree angle, both my legs are equal length. Therefore, sine and cosine are equal in value. These are the ones that we got root 2 over 2. That's the one that we got out of that sine of pi fourths. We can see this guy right here, sine of pi fourths. That's our root 2 over 2. This guy, I'm getting root 2 over 2, and we're squaring that guy as well. And it looks like I'm going to get here square root of 3 squared is just 3. 3 squared is 9. Over here, square root of 2 squared is 2. And 2 squared is 4. Again, yes, you should be able to add fractions right here. Definitely expect you to be able to do that. So I'm going to do here 3/9. I'm going to do times 4 over 4 plus 2/4 times 9 over 9 to get a common denominator. That's going to give me 12 over 36 plus 18 over 36, which is going to be 30 over 36. And it seems like that actually combines, we can simplify that pretty nicely. That's dividing both top and bottom by 6. It looks like we can land here at 5/6. And man, like, I think it's just kind of funny, like, I don't know, like this seems like a pretty gross trig expression up here. Came out to be like just a really clean fraction like that. So, start to expect that some of these things maybe are going to end up looking a little bit nicer than you expect. I think another thing that's a good takeaway from this, kind of in like summarizing what we just did, notice that all of our trig values of interest, some of them do involve square roots and a lot of them involve fractions because every trig function is a ratio of two side lengths. So it's all natural that they're all fractions. But at least the only two square root terms that we ever see are 2 and 3. Root 2 and root 3, you never are going to get like a root 7 from anything that you're doing with trig, basically, is kind of what I'm saying to you, from our special angles anyway. We're only ever expected to know these special angles right here. Right? So it's a little bit more limited. It seems like there could be lots of possibilities, and it's a little bit more limited than that. So we do end up with some nice expressions every once in a while, especially when we square things that had square roots. We get nice fractions, right? So let's summarize what we did here. Basically, the point is, you're expected to know all these, but it's not like memorize this giant table. It's like know your triangles and be able to come up with these without memorizing like literally hundreds of values. Nobody's supposed to be memorizing hundreds of values. Everybody's supposed to be coming up with techniques that they can use so that they can come up with these on their own. You draw a little triangle, say, oh yeah, it must be that. That's kind of our important thing there. So let's just kind of go on down the line here. I feel like I should like redraw these ones here, the 1, the root 2. So this is what you should be memorizing, is these triangles. And I think it's worth it to like walk through doing this again. I mean, this is how else are you going to like learn this, right? It's just like a little bit of repetition here is good. So I'm going to do the repetition right now as we fill up the table. The easy part of the table is the middle chunk, is the zeros and the 90s that are a little bit weird right now. But honestly, I think those are the ones that are going to be the easiest for you to remember after we cover the next two sections, where we're going to come up with really easy ways for us to remember why those are the way that they are. So first, maybe let's just do the whole pi-fourths row, or 45-degree row right here. The sine of 45 degrees looks like it's the 1 over root 2, which we know to write as root 2. What did you just do to me right there? Whoa, why is it moving around my stuff? Okay, I guess that's good there. Similarly, since both legs are the same length and sine and cosine just deal with opposite versus adjacent, this should also be root 2 over 2. Wow, I don't know what the heck it's doing to my stuff right there. Tangent is sine over cosine, and since these are equal to each other, this has got to be 1. And for our secant, cosecant, cotangent, we know that we just flip these guys. So flipping root 2 over 2 gives us 2 over root 2, which simplifies down to just root 2 and root 2 and 1 again. The reciprocal of 1 is 1. So that's what I got for my first triangle here. Now we do our 30s and our 60s. So let's do our 30 row. Sine of 30, opposite over hypotenuse, that's 1/2. Cosine of 30, adjacent over hypotenuse, root 3 over 2. Tangent is sine over cosine, so it looks like the dividing by 2's are going to cancel, leaving me with 1 over root 3. 1 over root 3, we did the algebra and determined that a better way to write that would be root 3 over 3 right there. It's the same as 1 over root 3, though. Now we just flip them all to get our cosecant, secant, and cotangent. Remember, sine and cosecant are buddies because one has a co and one doesn't. Cosine already has a co, so it's buddies with the one that doesn't over here. And tangent is always going to partner up with the other one that says tangent in it, right? So sine and cosecant are buddies, so this should just be 2. Secant is going to be the reverse of this, so it's 2 over root 3, but we rationalized that, and we got 2 root 3. What is it doing to me here over 3? Why is it flopping all those things around? I guess I shouldn't do a table anymore. That's very strange. And tangent, we're going to take the reciprocal of this guy, and our little bit of algebra told us that that was just root 3. And by the way, notice that if you do like 3 over root 3, that you could think of this as root 3 times root 3, because that's just root 3 squared is 3. And it's like they cancel, and you're just left with straight up root 3 as our other version of that guy there. Now, I know that for 60 degrees, I'm going to do this my more convenient way. I know that the sine of 30 is the same as the cosine of 60 because those are complementary angles. So I can right away just do this. All I did there was just switch these two boxes right there. And similarly, I know I also get to just switch the tangent and the cotangent boxes right here. Finally, I also know that I get to switch my secant and cosecant boxes right here. And notice that these do agree. Their reciprocal of cosine did give us 2 for the secant value right there, so that was good. So remember that there's a bunch of different tricks to say. All you really got to know is like 1 or 2 of these values, and that should be enough for you to fill out the entire rest of the table with all the other values. Just knowing a couple of these, you can say, oh, those are reciprocals. Oh, tangent sine over cosine. Oh, sine and cosine are going to be equal for all the 45 degree stuff. Our complementary angle thing. If you know everything about 30, then you by default know everything about 60. You just have to switch which trig function we're relating it to. Knowing just like a small number of these gives us all the rest. Finally, and these ones are, I'm going to kind of quote these a little bit more since there's not really a triangle that I'm picturing right here. But sine of 0 degrees, we're going to get 0. And sine of 90 degrees, we're going to get 1. And by the way, I want you to look at this column right now and see if you can identify some very special pattern in this column as I fill out the rest of these. So I know that 0 and 90 are complements, so it should be that the sine and cosine values switch for them, because sine of 0 should be cosine of 90 minus 0, which is cosine of 90. Right? Tangent is sine over cosine, which here is 0 over 1, and 0 over 1 is 0. But down here, tangent is sine over cosine, which is 1 over 0, which is undefined. Right? Cosecant is the reciprocal of 0, which doesn't exist, so it's undefined. But secant is the reciprocal of 1, so it's just 1. Finally, cotangent is the reciprocal of tangent, and the reciprocal of 0, undefined. And we're almost done. Now we're just doing our last ones here. Cosecant is the reciprocal of sine, and the reciprocal of 1 is 1, so we got that one. Secant is the reciprocal of cosecant, and the reciprocal of 0 is undefined. And for our very last one, cotangent is the reciprocal of tangent. Maybe a better way to think about this one is that our cotangent is going to be, instead of sine over cosine, it's going to be cosine over sine. That's our 0 over 1. So that's where we're going to get 0 for that cotangent value that we're looking at right there. Right? I did that right? Yeah. Right? Yeah, there's my cotangent of 90, 0 right there. Yeah. Why am I talking myself out of that? So I'm gonna bump this down a little bit so that you can notice a really special thing. And again, more things that are helpful for us to just try and remember the things that are going on right here. And the one special pattern that I feel like I see here is this. I think that it's easy to see the beginnings of a pattern here, and the pattern is even better than it looks. So importantly, notice that this is us increasing through these angles, right? 0, 30, 45, 60, 90. These are our special angles in order. This is the sine that we're looking at for these guys, but notice that the same pattern exists for cosine. Notice that the cosine column is the same. It's just the flipped version because the complements are top, bottom, opposite of each other here. So I'm hoping that what you're seeing is that this is 1 over root 2, root 2 over 2, root 3 over 2. Well, notice that this is the same thing. I'm going to kind of rewrite this. And I'm going to write all 5 of these slightly different. It looks to me like these numerators are going 0, 1, 2, 3. I don't know if I can finish the pattern down there, can I? That's kind of cool there, right? This is a kind of stupid way for us to write 0 as square root of 0 over 2. I'm doing that, though, to fit the pattern. It's stupid to write 1 as root 4 over 2, but the square root of 4 is 2, and 2 over 2 is 1. So it looks like there is this linear progression underneath the square root here across our 5 values of interest that we're ever going to see, right? Like, I mean, aside from getting some root 3 values out there from like some tangent stuff, these are sort of like our essential values that we get out from sine and cosine, at least right here, are these 5 values in a row, 0, 1, 2, 3, and 4 underneath the square root divided by 2. So again, and maybe this is like a better convincing to you that these are the only clean values that we're going to get, because if there were going to be more, then it should be some like number that's in between 0 and 1, or between 0 and 2, between 2 and 3, and there's not going to be a nice whole number that does that then, right? So some nice patterning that you can kind of identify for yourself also in here that's very, very helpful in thinking about the memorization. So now I'm seeing sine of 0 is root 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2, root 4 over 2. Those are the sine values for those 5 angles right there. And that's so again, your job is to come up with your ways to help you remember this. Technically, you're responsible for these 30 values right here and being able to get them from either degrees or radians. But what we don't obviously want to do is memorize this. If you memorize this table, you're crazy. You should be memorizing just these triangles and just the relationships between each of these functions. It's going to be way less information, way more practical. Our final thoughts on this today is that we're going to want to expand today's ideas to any angle, not just acute angles. So today we're just stuck from 0 to 90, but you should be thinking things like sine of 135 degrees, cosine of 27 pi. That's a huge amount of rotation. Tangent of a negative amount of rotation of negative angles. How do we make sense of all these things? So in the next 2 sections, we're going to keep expanding our definition of our trig functions. In a sense, alter the definitions, but we're going to retain all of our same old values while still getting it to make sense for some new values here, right? Now, while this is greatly increasing the number of angles for which we can compute sine, cosine, tangent, secant, cosecant, cotangent, it's still going to be the case that you're going to have to use a calculator for any of our non-special angles. It turns out all 3 of these are special angles that you're going to be able to compute the exact value of by just next class. So ultimately, you will be responsible for knowing the exact value of any of the 6 trig functions being applied to any multiple of our special angles that we saw today. But all the other ones are going to require a calculator. Sine of 22, it's just never going to look good. You're going to use a calculator for that for your entire life. There's never going to be a clean expression that represents that guy there. So we need to know which ones we're responsible for, which ones our calculator is responsible for. And again, our mission over the next 2 sections is to expand our view of these trig functions to beyond just defining ratios of side lengths of triangles here. So here's sort of our conclusion from today. We built these 2 triangles. So we constructed them mathematically in a sense, as well as constructing one slightly hokier triangle. But this triangle still is getting us some correct values, right? But it's like, you should feel weird about this because that wasn't like geometrically correct. That was sort of like an approximation idea there. But still, we were able to come up with exact values for a significant number of trig functions. And I guess my kind of final thought is, remember again that when we picked these numbers, that it was okay for us to just choose numbers here because of the fact that all of our trig functions are measuring ratios of the side lengths. So if you were to scale it up or scale it down, then when you still do the same division to get your trig ratios there, you would just get more fraction cancellation and it would reduce down to exactly these values once again right here. So you are responsible for these. Start thinking about how to know them. As you're doing your homework, what you should be doing is trying hard, like at least make a good guess every time. Don't just look all these up in a table. Every single one you should be like, okay, sine of pi thirds is 60 degrees. Sine of pi thirds is going to be root 3 over 2. And then you're like, and then you look at your table and you're like, sine of pi thirds. Oh, I got it, root 3 over 2. You should be doing this. This should be a practicing memorization thing. Almost every single person that's taking this class is taking this class because they need to take calculus. And I am 100% positive that no matter who you take calculus with or where you take it, absolutely every calculus professor on earth, or at least in the United States, I'm pretty sure on earth, absolutely expects every single student to be able to produce this chart essentially from memory, this table, on day one of calculus class. It is an expectation for the rest of your mathematical career that you know these. Obviously, you need some time to learn these, so like take that time, but like don't just look these up every time. You should be quizzing yourself constantly about memorizing these things to help yourself out, coming up with your own little ways as to how do you remember them. But again, we're going to get easier ways to remember these, particularly in section 6.5. We're going to get sort of a helpful visualization that's going to help you remember these too. So you are going to get more tricks to put in your tool bag to help you remember how these each work here. So that's it for me today. We're going to hit section 6.4 tomorrow, which is going to say, rather than just looking at angles from 0 to 90, we're going to get the full circle and then some. We're going to get forwards direction. We're also going to get negative rotation angles out there. Hey, Keenan, good to see you. Glad you're here. And yeah, it's always good to have people live here if you're looking to do that. But again, otherwise, I'll see you guys for 6.4 tomorrow, and we will expand our angle repertoire in our next video here. Have a good one, everybody. I'll see you in section 6.4.